Welcome to video lectures. I am Karanam Rao, Assistant Professor, Vijayanagara College, Hosapete. And today's topic is on origin of spectral lines. Let us consider an hydrogen atom in the normal state. The electron is at its lowest energy state, say n is equal to 1. When an energy is given to it, then only quantized amounts of energy are being absorbed by the electron. Then the electron absorbs this energy and is raised temporarily to a higher orbit. That means the electron moves from lower to the higher energy state. When the electron moves from lower to the higher energy state, then the atom is said to be excited. The excited state of an atom is most unstable state, and within a very short interval of time, say about 10 raised to minus 9 seconds, the electron relaxes to a lower energy state. During this process, the difference in energy between the two orbits emits as electromagnetic radiation. If E1 and E2 are the energies of the electron in the orbits N1 and N2 respectively, then if nu is called nu, not V, nu is the frequency of electromagnetic radiation emitted when the electron relaxes from N2 to N1. Then, according to Bohr's frequency condition, h nu is equal to E2 minus E1, where E2 is the energy of the electron in the second energy state and is given by minus mz square e to the power of 4 divided by 8 epsilon naught square n2 square h square. E1 is given by minus mz square e to the power of 4 divided by 8 epsilon naught square n1 square h square. And h nu is given by E2 minus E1. On substitution of these values of E1 and E2, we get minus mz square e to the power of 4 divided by 8 epsilon naught square h cube into 1 by n1 square minus 1 by n2 square, where lambda is called as wavelength of the emitted radiation, where nu is equal to c upon lambda, where c is the velocity of electromagnetic radiation and nu is given by c by lambda, where c is the velocity of electromagnetic radiation in free space. When you substitute, then c by lambda is equal to mz square e to the power of 4 by 8 epsilon naught square h cube into 1 by n1 square minus 1 by n2 square, or 1 by lambda is equal to mz square e to the power of 4 by 8 epsilon naught square c h cube into 1 by n1 square minus 1 by n2 square, where nu is called as the wave number of the spectral lines. That is, wave number is called as 1 by lambda. That means reciprocal of wavelength is called wave number, that is represented as nu bar. It has to be nu bar. It has to be written over the letter, the line. Line over the letter indicates bar. Line V bar, nu bar is called as wave number of the spectral lines. And R is equal to m e to the power of 4 by 8 epsilon naught square c h cube is called Rydberg constant. When we substitute this value of the constant, then we get one more constant, that is given by 1.097 into 10 raised to 7 per meter. That means Rydberg constant is a constant of constants, where m is the mass of the electron, which is a constant. E is the charge of the electron, which is a constant. Epsilon naught is the permittivity of free space, which is a constant. C is the velocity of light, constant. H is the Planck's constant. So as this value of R is obtained out of constants, therefore Rydberg constant is a constant of constants. Therefore, nu bar is equal to R into z square into 1 by n1 square minus 1 by n2 square. This is said to be the Rydberg's formula for spectrum of hydrogen atom, or it is the Rydberg's formula for spectral series of hydrogen atom. As Z is equal to 1, for hydrogen atom, then nu bar is equal to R into 1 by n square minus 1 by n2 square, which is said to be the Rydberg's formula. Now we shall understand what are the spectral series of hydrogen atom. There are 5 spectral series of hydrogen atom, namely Lyman series, Balmer series, Paschen series, bracket series and Fund series. When the transition of an electron which when takes place from higher energy state to the first orbit, then these spectral lines are said to be the Lyman series, which happens to be in the ultraviolet region of electromagnetic spectrum. The Balmer series, when the transition of an electron which when takes place from higher to the second orbit, is called Balmer series. These spectral lines are in the visible part of electromagnetic spectrum, where H alpha, H beta, H gamma, H delta are the first, second, third and fourth spectral lines, in which brightness and separation between the spectral lines decreases gradually. The Paschen series, when the transition of an electron which when takes place from higher to the third orbit, then it is said to be Paschen series, which is in infrared region of electromagnetic spectrum. Bracket series, when the transition of an electron which when takes place from higher to the fourth orbit, then it is said to be bracket series, which is again in the infrared region of electromagnetic spectrum. The Fund series, the spectral series which when obtained by the transition of electron which when takes place from higher to the fifth orbit, then it is said to be the Fund series, and they are in the infrared region of electromagnetic spectrum. Now you are observing the spectral series here. That is, in Lyman series, when the transition of an electron which when takes place from higher to the first orbit, they are said to be Lyman series, which is in the ultraviolet region. The Balmer series, when the transition of electron which when takes place from higher to the second energy state, it is said to be Balmer series, which is in the visible region, in which the lines H alpha, H beta, H gamma, as the separation increases by decreasing the separate brightness. Therefore, brightness and separation decreases gradually. Paschen series, when the transition of electron which when takes place from higher to the third orbit, then it is said to be Paschen series, which is in near infrared region. Bracket series, when the transition of an electron which when takes place from higher to the fourth state, it is said to be bracket series, which is in far infrared region. The transition of electron which when takes place from higher to the fifth energy state, it is said to be Fund series, again which happens to be in the far infrared region. So these are all said to be spectral series of hydrogen atom. Thank you.